This is GATE 2015 set to electrical question number 36. It says two semi-infinite conducting sheets are placed at right angles to each other as shown in the figure. A point charge of plus q is placed at a distance of d from both sheets. Net force on the charge is given by q square by 4 pi epsilon naught k by d square. Now k value is asked. So for this given configuration we need to find out the net force on charge q, right? Now first, in order to solve this question you need to know Coulomb's law, that if these are q1 and q2, two charges are placed and separated by distance d, then force on charge q2 equal to force on charge q1 equal to, that is, their magnitudes are equal but directions will be decided based on their polarity. So magnitude can be written as 1 by 4 pi epsilon naught q1 q2 divided by distance square. Now direction, if q1 q2 are of similar polarity, then type of force will be repulsion. So if this is the case, repulsion is the case, then force will push charges apart. So in that case, what do you think will be the force direction? So this will be like this: q1 q2 is there separated by distance d, and this is like this. Now if q1 q2 are opposite polarity, then attraction will be the force, and this will pull together the charges. Now like this, q1 q2, and the force direction will be like this, right? And now in order to find this direction vectorially, what we can do, this is the coordinate system and this is position of q1 and q2. Now position vector from origin connecting q1, let's say be r1, and position vector connecting q2 is r2. So this direction can be written as r1 and r2 difference. This is the direction of the, for example, let's say x hat, or rather let's not say x hat, let's name that r hat. So this is r hat, but since this is unit vector, we need to multiply the direction only, not the magnitude. So divided by mod of r2 minus r1. So this is the unit vector along this direction. r2 minus r1 is the vector, and dividing it by its magnitude, this is the unit vector. Multiplying it with that value q1 q2 by d square, we get the complete electric field vector, that is E vector, multiplied by that charge q2. So that is force, right? We get the force like this. So coming to another useful data, if we have semi-infinite sheets, semi-infinite means these are infinite sheets. Now for this sheet you just cancel this one, and for this sheet you just cancel this part, so you are left with this sheet configuration. Now with this you have a charge q, let's say it is placed at d comma d. Now this distance is also d, this distance is also d, as is shown in the figure, right? Now we have to find the force on q due to these two semi-infinitely charged plates. Now these are conducting sheets. Now this is equivalent to placing a plus q charge here and following the method of image charge. Now similarly this is minus q, because when you take the image you need to reverse the polarity. Similarly this interface, you take the image of this, where you get plus q, and again you take the image of this, you get minus q. So always take the image along this or along this, that is the interfering surface, that is the conducting surface. Along this only you take the reflection. Along this you take any of this reflection, you get minus q. Along this you take its reflection, you get minus q, and along this you take this reflection, you get plus q. So along these surfaces you need to take the reflection and you get this configuration. So these two configurations are equivalent configurations. You will now need to find the force on this charge due to these other three charges, which are equivalent and alternative method for representing this conducting surface. Solution: this is the charge on which we find the force. So this is minus q, as per method of image charge this is plus q, and similarly this is minus q. This is d comma d, this is minus plus d comma minus d, this is minus d comma minus d, this is minus d comma plus d, and this is origin. So now you see this distance is d, and this distance is also d, and this distance is d. Now you see this minus q will attract this plus q. Let's name this f1. This plus q along the diagonal will repel this, so name this f2, and this minus q will pull it, so f3. Now f1 can be written as q square by 4 pi epsilon naught, it is q1, then q2, and then 4 pi epsilon naught. You can see the direction, right? So you just take the magnitude first and then decide the direction vectorially. So q1, q2, q is q square by 4 pi epsilon naught d square. So d is 2d, that is the distance between this to this is 2d. So you take 2d square, which is 4d square. Now direction is along minus ax hat, that is unit x vector. So this is x, this is y, plus now f2. So what is f2? f2 is along ax plus ay hat divided by root 2. So this is unit vector along this direction, and its magnitude is q square by 4 pi epsilon naught. Now what is d? This is 2 root 2, because this is root 2d and this is root 2d. So 2 root 2 d, that is whole square. So what is that? 8d square. Now f3 is along the minus ay hat downwards, so minus ay hat. So q square by 4 pi epsilon naught, and this distance is 2d, so 4d square. Now f net equal to f1 plus vectorially plus f2 plus f3. So it is coming out to be. Now see the ax hat first and then ay hat. So you will have in two components, just group them, ax and ay terms. So x terms are 1 by root 2 into 8 plus minus 1 by 4, and you have ay terms as 1 by root 2 into 1 by 8 minus 1 by 4, and over multiply it with q square by 4 pi epsilon naught d square. So actually this is being asked in the question. This is the value of k that you need to multiply with q square by 4 pi epsilon naught d square, right? Q square by 4 pi epsilon naught d square. Now k value is this. This is the factor, numerical factor. So now can be written as 1 by 8 root 2, 1 minus 2 root 2 ax hat plus 8 root 2 again 1 minus 2 root 2 ay hat. So this is the value of k. 1 minus 2 root 2 by 8 root 2, 1 minus 2 root 2 by 8 root 2. Ax cap is I cap and ay cap is z cap. So D is the correct option, right? Thank you.